Good afternoon, everyone. I hope that everybody had a great weekend and that you're doing well today. Today we're going to be moving on and looking at integration by parts, which is a different technique of integration. And this is lesson 31.18, part A. We're going to continue with this next time as well. This lesson can be found on page 19 of your current lesson handout. When we studied integration using substitution, I was very careful to not use the word part. I always used the word piece. And with substitution, there was this general guideline that said if one piece of the integrand is contained within the derivative of another piece of the integrand, then integration by substitution would probably be beneficial. So in general, with this method of integration, and I want to stress that this is a general guideline, it's not always going to be the case, but in general, if you choose one part of the integrand and it were to get simpler if you differentiated it, then integration by parts is probably, but not always, the way to go. By the way, when we talk about a part of the integrand in this method of integration, it's a factor as well. For example, the following two integrals contain integrands that have a part that becomes simpler when differentiated. So when I take a look at the integral of x sine x dx, x becomes simpler when I differentiate it. When I take a look at the integral e to the 4x multiplied by 3x plus 2, 3x plus 2 is a part of the integrand that gets simpler when I differentiate it. I want you to notice that x in the first integral is a factor. As well as just being, quote, a part, it's a factor. The other factor is sine of x. And in the second integral, 3x plus 2 is a factor. And I want to highlight something else that I hope will be helpful for you. The integral of x sine x has two factors in the integrand, x and sine x. The integral e to the 4x multiplied by 3x plus 2 has two factors in the integrand, e to the 4x and 3x plus 2. And there will always be two factors when you're using integration by parts. The factor that I've highlighted in yellow is the factor or part that gets simpler when you differentiate it. Integration by parts should be thought of as simply applying a formula. Now, I'm not going to go through a proof of where the formula comes from. I don't think it's that important. We're going to discover that the formula will work. And basically what the formula allows us to do is take an integral that we don't know how to anti-differentiate and change it into something that contains an integral that we do know how to anti-differentiate. And the formula using Lagrange's notation, which is the function notation, is the integral of f of x multiplied by g prime of x dx is equal to the product of f of x and g of x minus the integral of g of x times f prime of x dx. And I know that when you look at that, it becomes very, very confusing. A little bit later on, we'll look at what it appears as if we use Leibniz's notation. I prefer to use Leibniz's notation, but I think as a student, it's better to start off with Lagrange's notation. All right, so notice that one part or factor of the integrand in the original integral is chosen to be f of x. It's chosen to be called something that is a function of x. But the other part is chosen to be called the derivative of a different function of x. And our goal is to rewrite that integral as an equivalent expression using the information on the right. So how does that work? Well, before we get to a specific example, I want you to notice that you have f of x here. And what f of x is that function that you have chosen in yellow on the left. I also want you to notice, however, that you have f prime of x on the other side. And what f prime of x is the derivative with respect to x of the thing that you chose as being f of x. On the other hand, on the right-hand side, you also have g of x. Now, g of x appears in two places in this formula. And what g of x is the antiderivative of the thing that you chose for g prime of x. G prime of x is the blue item that's been highlighted. So g of x would have to be the antiderivative of g prime of x. And this is going to be a lot to process because on the one hand, part of what you choose has to be differentiated to move forward. And on the other hand, part of what you chose has to be anti-differentiated to move forward. Now, let's look at a specific example because I think the example will help you understand in the end why this works, and it will also help you get organized in terms of trying to keep track of all of these parts. So we are asked to integrate x sine x dx, which I'm simply going to rewrite to drive home the fact that there are two parts. There are two factors to this integrand. One of the factors is x and one of the factors is sine of x. Now, the thing that you choose for f of x should always be the thing that gets simpler when you differentiate. So x gets simpler when you differentiate it. Sine of x doesn't get simpler when you differentiate it. It just changes into a different trigonometric ratio. What that means, everybody, is that you have no choice other than to say, I'm going to call sine of x g prime of x. Now, if you look at the top of the page, in order for me to write out what this original integral is equal to, I need to know the following things. I need to know f of x. Well, I do, it's x. I need to know g of x. Well, I don't know g of x, but if I anti-differentiate g prime of x, that will give me g of x. And by the way, when I anti-differentiate g prime of x to get g of x, I will also know this within our substitution on the right. And I also need to know f prime of x. Well, how am I going to find f prime of x? That's a breeze because f of x is x. I can find f prime of x. So that's why the schematic I have on the board I think is useful. Whatever you choose for f of x, you are going to differentiate to determine f prime of x, and you get 1. F of x is x, so the derivative of x is 1. You need to do that because you're going to have to replace f prime of x in the formula with something, and it's going to be replaced with the number 1. In order for me to proceed here, I have to take sine of x, which is g prime of x, and anti-differentiate it. The antiderivative of sine of x is negative cos of x, and I would ask you, if you need to just pause the video and process that. The antiderivative of sine of x is negative cos of x because when you differentiate negative cos of x, you get positive sine of x. So now what does this formula say? This formula says that our original integral will be equal to the product of f of x and g of x. Well, that's the product of these two things. So it will always be the product of those two things, which will be x multiplied by negative cosine of x, and then it says minus the integral of g of x times f prime of x. So g of x times f prime of x is the product of these two things. So we have to subtract the integral of the product of those two. And that will be the visual pattern all the time. You will always be multiplying these two and subtracting the integral of the product of these two, always. So now I can go ahead and do that second half of my formula. I will have minus the integral of the product of g of x, which is negative cos x, multiplied by f prime of x, which is 1. Of course, we throw in the dx for good measure. I can simplify this now. The integral of x sine x dx equals negative x cos x plus the integral of cosine of x dx. And what I've done in going from that last line to the present line is I've factored the negative 1 out of the integrand. So I am factoring out of negative cos x times 1 times dx this negative 1, and I'm combining it with the negative 1 that is outside of the integral to get a positive integral of a positive integrand. And this is the beautiful thing about integration by parts. When you take a look at this, you have no idea how to proceed. I mean, really think about this for a second, everybody, please. What is it you differentiate to get x sine x? That's an impossible question to answer. You can't just turn that around in your head and say, oh, I differentiate the following to get x sine x. At least I can't, and I've never met anybody who can. But when you take a look at this integral, no problem. You can anti-differentiate cos x. So to finish this off, we have the integral of x sine x, and when we applied the formula for integration by parts, we got negative x cosine x plus the integral of cosine of x, which is sine of x. Don't forget your constant. You forget your constant next year, and your TA who's marking your papers will be taking off half a mark everywhere. So let's go back to this idea that if I said to you, all right, let's figure out what this integral is equal to. I don't think there's anybody who's watching this video that would know the integral of x sine x dx, and I just realized that I forgot my dx in here, which there should be a dx. There's nobody watching this video who's going to say, oh yeah, the antiderivative of x sine x dx is equal to negative x cos x plus sine x. I mean, you might learn something from this video and later on be able to figure that out. Let's prove that that's the case now, because if that is correct, then the derivative of what we got, which is negative x cos x plus sine x plus our constant, if that's correct, then the derivative of that should give us x sine x. So how am I going to differentiate negative x multiplied by cosine of x? Well, I'm going to have to use the product rule. And in fact, everybody, if you were to look at a proof of this, which I would do in class if we were in class, it turns out integration by parts is actually the product rule in reverse. But let's find the derivative of negative x cos x using the product rule. The derivative of the first, which is negative x, is negative 1 multiplied by the second, plus the first, which is negative x, multiplied by the derivative of the second, which would be negative sine of x. Now we move on to the next term, which is sine of x. The derivative of sine of x is cosine of x. The derivative of my constant is 0. what we end up with is negative cosine of x plus x sine x plus cosine of x. Well, the negative cosine of x plus the cosine of x equals 0. And then we have that middle term, which is x sine x. Well, that's what we're supposed to get, and that's what we did get. So what the integration by parts formula does is it allows a bunch of terms that pop out of the application of the product rule to cancel with each other, leaving only a product that was the integrand that we were trying to anti-differentiate. All right, let's try example 2, the integral of e to the negative 2x multiplied by 3x plus 4 dx. Remember that the thing you want to choose for f of x, there will be an exception, okay? And the exception will be in example 3, so it's coming up quick. But generally speaking, the thing that you want to choose for f of x is the factor or part of the integrand which gets simpler when you differentiate it. And 3x plus 4 gets simpler. That means that the other part is e to the negative 2x, and e to the negative 2x must be equal to the other part, which is g prime of x. So we're choosing something for g prime of x. And we're choosing something for f of x. The product of those two things that we choose have to complete the entire integrand. You can't have anything left over. This is not like substitution where you might have other pieces that you don't worry about. These parts have to multiply to give the integrand. So now how do we proceed? What we have to do is differentiate what we chose as f of x. That's pretty simple. We have to anti-differentiate what we chose as g prime of x. Not as simple, but doable. I would ask you to again pause the video here and contemplate why the antiderivative of e to the negative 2x is negative 1/2 e to the negative 2x. The reason is that when you differentiate negative 1/2 e to the negative 2x, since it's a base e exponential function, you get the exact same thing, which would be negative 1/2 e to the negative 2x, but then you multiply by the derivative of the argument, which would give you a negative 2, and that negative 2 would cancel with the negative 1/2. So now remember, when we rewrite this, it is always the product of these two minus the integral of the product of those two. So the integral of e to the negative 2x multiplied by 3x plus 4 dx. And I'm really using the formula at the top of the page here. F of x times g of x is what I have to write down. But f of x times g of x is this. So I'm going to have 3x plus 4 multiplied by negative 1/2 e to the negative 2x. Then I have minus an integral, and the integral will have a product that is the product of these. So the integral will be (3) multiplied by negative 1/2 e to the negative 2x dx. The order that you multiply them in doesn't matter. So where do we proceed from here? Well, I have a whole bunch of constants contained in that integral. So now I have the integral of e to the negative 2x multiplied by 3x plus 4, which is what we are after, is equal to 3x plus 4 multiplied by -1/2 e to the negative 2x. Then I have minus, but I can take that 3 and that -1/2 and move those factors out in front and have plus 3/2 the integral of e to the negative 2x. There's that beautiful thing about that property of integrals that we talked about before. By factoring those constants out, I don't have to clutter my brain with more information than I need. Ultimately, what I have to do, everybody, is anti-differentiate e to the negative 2x. Then I can multiply by 3/2. So what do we get? The integral of e to the negative 2x multiplied by 3x plus 4 is equal to, I'm just going to switch the order of these two factors, -1/2 e to the negative 2x times 3x plus 4. Then I have plus 3/2. Now what is the integral of e to the negative 2x? We already did that. It's -1/2 e to the negative 2x plus our constant. So let's clean this up and then we will check it. So let's clean this up and then we will check it. We're claiming the integral of e to the negative 2x multiplied by 3x plus 4 dx is equal to -1/2 e to the negative 2x times 3x plus 4. Then we have minus 3/4 e to the negative 2x plus our constant. If we differentiate what we believe to be the answer, it has to give us the original integrand. So it's very easy to check. I'm not suggesting that you want to check these every time, but this is only our second example, so I'm going to verify it with you. The derivative with respect to x of -1/2 e to the negative 2x times 3x plus 4 minus 3/4 e to the negative 2x plus our constant. That's what we're working on. By the way, I believe as a teacher, I believe that when you see how the derivative of our answer is found, you might gain a deeper understanding of why this method is working. I'm going to have to use the product rule. When I differentiate this entire term, -1/2 e to the negative 2x times 3x plus 4, I have to use the product rule. All right, so what is the derivative of the first? It will be -1/2 e to the negative 2x multiplied by -2, which is the derivative of the argument on the base e function, times the second, which is 3x plus 4, plus the first, which is -1/2 e to the negative 2x multiplied by the derivative of the second, which is 3. Then minus, I still have to differentiate 3/4 e to the negative 2x, which would be 3/4 e to the negative 2x multiplied by the derivative of the argument of the base e function, which is -2, plus the derivative of the constant, which is 0. So what do we get? In the first term, the -1/2 multiplied by the 2 cancels to give us 1, so we are left with e to the negative 2x multiplied by 3x plus 4. The second term is -3/2 e to the negative 2x. And the last term, surprise, surprise, is +3/2 e to the negative 2x. So this is a wash. It doesn't count. All we are left with is this, which was our original integrand. So it's correct. Let's take a look at the final example. The final example is going to be completed using Leibniz's notation, differential notation. I just like this so much better. the integral of u dv equals uv minus the integral of v du. It's easier, it rolls off the tongue a little better, and the other thing is algebraically everything fits. When we were doing the first couple of examples, what we had to do was always remember to put that dx in there. So in this, u is the thing you differentiate to get du. In other words, everybody, in this form, u is chosen as the function and dv is chosen as the derivative. It requires a little different viewpoint, but that's essentially what's going on. We're still choosing u so that we can put u here. We're still choosing dv so that we can find v to put here and here. And we're choosing u so we can find du to put du here. We're still choosing parts of the function to differentiate and anti-differentiate. So if you did example 1 with Leibniz's notation, you would choose x as u, which would mean du is dx. You would choose sine x dx as dv, and you would get negative cos x as v. One of the things I like about this is that the thing you choose for f of x is u. That's pretty straightforward. But the thing I really like about it is the thing that you choose for dv, which in this case is sine x dx, is everything else. It actually includes the dx. So algebraically, it makes more sense. It's still the product of these two minus the integral of the product of those two. So this would be equal to x times negative cos x minus the integral of dx times negative cos x, which would give negative cos x dx. You still get the same result. If you did this with example 2, you would have chose 3x plus 4 equals u. That would mean du is 3 dx. dv would have been e to the negative 2x dx, which means v would have been negative 1/2 e to the negative 2x. This would be equal to the product of 3x plus 4 and negative 1/2 e to the negative 2x minus the integral of the product of 3 dx and negative 1/2 e to the negative 2x. You get the same thing. So let's try a third example, but we're going to use the notation that I just talked about. And there's also something else that's different here. I told you that the thing you choose for u is almost always the thing that gets simpler when you differentiate. The exception is if you have the natural logarithm appearing in the integrand. You're going to choose ln of x as being u. Now, one of the reasons why you have to do that is if you didn't and you chose ln of x equals dv, and I said to you, anti-differentiate ln of x, your head would start to hurt. You don't know how to anti-differentiate ln of x. You will learn how to anti-differentiate ln of x, but you don't know how yet. So you have to choose the natural logarithm of x as u, which means x cubed dx is dv. What is the derivative of ln of x? It's 1 over x dx. What is the antiderivative of x to the 3 dx? It's 1/4 x to the 4. We want the product minus the integral of the product. That gives us the integral of x cubed ln x dx equals 1/4 x to the 4 ln x. The order that you multiply these doesn't matter. Minus the integral of 1/4 x to the 4 times 1 over x dx. The integral of x cubed ln x dx equals 1/4 x to the 4 ln x minus 1/4 the integral of x cubed dx. We can factor that quarter out. That integral, by the way, the antiderivative of x cubed dx, is so easy to solve. In fact, you've already done it. It's 1/4 x to the 4. So our integral, the integral of x cubed multiplied by the ln of x dx, will be equal to 1/4 x to the 4 ln of x minus 1/4 times that integral, which we figured out was another 1/4 x to the 4. Don't forget your constant. The integral of x cubed times ln x dx turns out to be 1/4 x to the 4 ln x minus 1/16 x to the 4 plus your constant. If that's correct, then when we differentiate with respect to x, 1/4 x to the 4 ln x minus 1/16 x to the 4 plus our constant, we should get x cubed ln x. Again, if you're going to check these, and you don't have to, I'm just checking for completeness sake, then it will always involve a product rule. The derivative of 1/4 x to the 4 is x cubed, multiplied by the second, which is ln x. By the way, that's what we want to get, right? That's our integrand. Then I have plus the first, which is 1/4 x to the 4, times the derivative of the second, which is 1 over x. Then I have to subtract the derivative of 1/16 x to the 4. If I swing that 4 down, I get 1/4. I drop 1 from the exponent, I get x cubed. Plus, of course, the derivative of my constant, which is 0. This becomes x cubed ln x plus 1/4 x cubed minus 1/4 x cubed. Well, again, the two terms cancel, reducing to 0, 1/4 x cubed minus 1/4 x cubed, which gives you x cubed ln x, which is what we started off with as being the thing to anti-differentiate, so it works. And again, don't spend all your time double checking things. I just think for the first few that we do, it's interesting to see how it works. So on the next page is a whole plethora of problems that you can do using parts. The problems that you should be able to do after today's examples are numbers 1 through 14, 21, 26, 35, and 37. I wouldn't recommend doing them all. I think if you did 4, 5, 7, 8, 9, and 14, that's good enough. Over the next day or two, we're going to be doing more problems where we integrate by parts. And there will be other little twists and turns and tricks that we will be covering to make your job a little bit easier. So I hope that made sense. Have a wonderful rest of the day, you guys, and we will talk to you soon. Take care.